Welcome to this video tutorial on regression. Now what we're going to look at this time is multiple linear regression. But first, let's remember in simple linear regression, we're interested in when we have one x variable that's going to explain the variation in y via a line, and this is the equation of a line. yi equals beta 0 plus beta 1 xi. This is the intercept, this is the slope, and what we're interested in now is what if I have more than one x? Okay, suppose I have variables, lots of them, that might influence it. Like x1 is what we're going to call the first one, and we're going to subscript it with a 1, x sub 2, all the way down to x sub k. So there are going to be k of these possible variables that are independent variables that may have an influence on y. Now to set this up, we just need to modify what we have here by making it a little bit bigger. So we take the multiple regression with the following model. We're going to have a beta 0, which is the intercept again, but we're going to have a beta 1, a beta 2, all the way out to beta k, and these are going to be the regression coefficients associated with each one of these variables. Now, x sub 1 here is observed as x sub 1 sub I. This I corresponds to the ith observation. x2 sub I corresponds to the ith observation, and so on, to keep everything lined up. All right, we're going to look at this JobHappiness.csv dataset that's linked in the description below. So we're right now just going to look at hours worked and distance to work. So we're going to want to look at these two particular variables. We'll look at the other ones in subsequent videos. Okay, so that's what I just said there. So x1 is going to be the hours to work, and x2 is the distance to work. So we can actually interpret these. So because our multiple linear regression only has two regressors, x1 and x2, we can say beta 0 is the expected value of y when both x1 and x2 are 0. Beta 1 is the expected increase in y when x1 is increased by 1 unit and x2 is held constant, meaning we're only changing x1. Beta 2 is the expected increase in y when x2 is increased by 1 unit and x1 is held constant. So that means we're only going to change x2. And you'll often hear people say all else held constant or all else equal. That's what their meaning is. We're not going to change the other variable. We'll only look at the effect of x2 when the other ones are held to a constant value. All right, so we can look and see what these variables look like against each other. So happiness is our outcome, so it's going to be on our y-axis on both of the plots. We've got hours worked, and we've got distance to work. And if you look here, there's a little bit of a pattern, but not a great pattern. You can see that corners are empty, and maybe suggesting there's a positive relationship. Here, maybe the corners are empty, suggesting a negative relationship, but it's not really strong like we've seen in the past. We could calculate the correlation coefficients with each of these. So this one is 0.568 for when we used hours by itself, and it's negative 0.137 when we use distance. And that looks like it's very weak. And even this one would be considered weak. So we don't really have strong correlations here. So let's go to SPSS and fit the model. Okay, this is the Job Happiness dataset. It's found in the JobHappiness.csv dataset that is linked below in the description, so you can get a hold of it if you wish to follow along. All right, we're using multiple linear regression here, and what we want to do is we want to go to Analyze, just like we have in the previous videos. We're going to go down to Regression, and we find that linear is what we want to use. We're going to put happiness is our dependent variable. In this case, we're only interested in 2 because we're trying to keep it simple. So we're going to put hours that it takes to hours of week of work and the distance traveled to work. Now we're not going to do anything else other than just click OK here and get the output. Okay, so here we have the output. You can see the coefficients are down here. Now we're going to switch over to the slide so we can look at this a little bit closer. All right, so here's the output that we generated in SPSS. So here we have our coefficients, our constant, the coefficient for hours, and the coefficient for distance, and we can build our regression model. So beta 0 is equal to 14.136. This number right here. Beta 1 is 0.199. Beta 2 is negative 0.076. You can see exactly where I've got the numbers from. So that gives me the following regression equation. So 14.136 plus 0.199 times x1, or the number of hours worked, minus 0.076 times x2, or the distance to work. So if we want to interpret this is what we need to be able to do. If someone worked no hours, that's x1 equals 0, and lived at work because their distance to work is 0, then we would expect their happiness index to be around 14. Does that seem reasonable? No, that's kind of nonsense, because if you don't work, why would you live at work? Okay? For beta 1, for each 1 hour increase in hours worked, we expect a 0.199 point increase in the happiness index, given all other variables are held constant. Okay? And for each additional mile from work to home, we expect a 0.076 point decrease. Notice I took the negative and turned it to a decrease and didn't put the negative here. That way things read a little better in the happiness index, given all other variables are held constant. Okay, so this is what we can do, is we can just run these regressions, and we can get the equations, and we can interpret the coefficients. They mean something. In addition, we can also test the coefficients, because it gives us a t-value, a significance already over here, so we could use those. What are we trying to test? Well, we're trying to test whether or not the variable is significant. But we need to be careful, because the p-values will only be valid in the presence of the other variable. So if you put other variables in this model, you'll see the p-values change. So for example, the p-value for h naught, beta 2 equals 0, is 0.326. Most people would say that's not statistically significant. However, if you were just to run regression with just x2 in it, the distance, you get a p-value of 0.331. So they will change depending on the data set that you're using, meaning when I say the data set, I mean the other predictors you're putting in.